Welcome back. Let's look at some examples involving the angle between two vectors. Alright, so here's our first example. We want to find the angle between vector v, which is the position vector of the point 1, 1, and vector u, which is the position vector of the point 3, negative 3. And so if you want to find the angle between two vectors, you need to know the following formula. Cosine theta, where theta is the angle between vector v and vector u, is equal to the dot product of vector v and vector u divided by the magnitude of vector v times the magnitude of vector u. All right, and so you can set up this formula using the dot product of vector v and vector u and their magnitudes, but then to actually solve for the angle, we will need to use the inverse cosine function on both sides of the equation. All right, and so we'll get to that, but let's just start with finding what we need to set up this formula. All right, if we want to find the angle between these two vectors, we need to know what the dot product is for those two vectors, and we need to find each of those vectors' magnitudes. And so let's start with that. Let's find the magnitude of vector v and the magnitude of vector u. And so the magnitude of a vector is equal to the square root of the sum of the components squared. So for vector v, the components are 1 and 1, so we'll have 1 squared plus 1 squared. And then for the magnitude of u, we'll have the square root of 3 squared plus negative 3 squared, right? The components of vector u are 3 and negative 3, so the sum of our components squared will be 3 squared plus negative 3 squared. Okay, now if we simplify each of these magnitudes, 1 squared is 1, so we have 1 plus 1 underneath this square root, so this is equal to the square root of 2. And then for the magnitude of vector u, 3 squared is 9 and negative 3 squared is 9. So this is equal to the square root of 9 plus 9, which is 18. So we'll have the square root of 18. All right, now if you want to, you can simplify this further. 18 has a factor that is a perfect square, right? 18 is equal to 9 times 2. So you could say that this is equal to the square root of 9 times 2. And we know that the square root of 9 is 3. So this would be equal to 3 square roots of 2. Okay, so the magnitude of vector v is the square root of 2, and the magnitude of vector u is 3 square roots of 2. Now all we need to set up this equation is the dot product of vector v and vector u. And so let's work on that next. The dot product of vector v and vector u will be equal to the sum of the product of corresponding components. In other words, we're going to multiply the x components together for our vectors and then add that to multiplying the y components together. So that will look like this. We'll have 1 times 3, and then we'll add that to 1 times negative 3. Right? We multiplied the x components together, which were 1 and 3. So we have 1 times 3. And then we added that to the product of our y components, which are 1 and negative 3. So we have 1 times negative 3. So this is equal to 3 plus negative 3, which is just going to be equal to 0. All right, so the dot product of vector v and vector u is equal to 0. And so now we can use that value as well as our two magnitudes to find the angle theta between vector v and vector u. So here's what we'll have. We'll have cosine of theta is equal to the dot product of vector v and vector u, which is 0. So we'll have 0 divided by the magnitude of vector v times the magnitude of vector u. So we have the square root of 2 and 3 square roots of 2. So I'll write that in. We have the square root of 2 times 3 square roots of 2. But that doesn't even matter because 0 divided by anything is just 0. So what we have here is that cosine of theta is equal to 0. And so now, to solve for our angle of theta, what we need to do is use the inverse cosine function. We'll take the inverse cosine of both sides of the equation. And so taking the inverse cosine of cosine will cancel each other out. So we're just going to be left with theta equal to inverse cosine, or arc cosine, that's another way that you could express that, of 0. And arc cosine of 0 is equal to pi divided by 2. So what we find here is that theta is equal to pi divided by 2. And that's in radians, of course, pi divided by 2 radians. But that would be equivalent to 90 degrees if you were working in degrees and not radians. All right, so both of those answers are correct, depends on the units that you want to use, but the angle between vector v and vector u in this problem is pi divided by 2 radians, or 90 degrees. And that's actually an interesting result because when the angle between two vectors is pi divided by 2, or 90 degrees, what that means is that those two vectors make a right angle and are therefore perpendicular, right? If we were to graph these two vectors, you would find that they would look something like this. You'll have vector v pointing in one direction, and then vector u will be pointing in another direction, but they will make a right angle with each other. All right, the two vectors are perpendicular because the angle between them is 90 degrees. And if you watched my lesson video on this topic, you might have been able to conclude that even faster than we did here, because we talked about how if the dot product of two vectors is equal to 0, then those vectors are perpendicular. They will have an angle of 90 degrees, or pi divided by 2 radians. All right, so the moment that you see that the dot product between two vectors is 0, which it was in this case, you can immediately conclude that those vectors are perpendicular and therefore have an angle of pi divided by 2 radians, or 90 degrees. Okay, let's take a look at another example. Next up, we want to find the angle between vector A and vector B, where vector A is equal to 4i plus 2j plus k, and vector B is equal to 2i minus 3j. All right, now in this case, our vectors are given to us in standard unit vector notation. The only difference is that the x, y, and z components are now the coefficients of our standard unit vectors I, j, and k. All right, and you'll also notice in this problem that we're now working with 3D vectors since vector A has an I, j, and k term. So we're going to have an x, y, and z component for vector A. Now, vector B only has an I and j term, so that just means that the z component is 0. So you want to keep that in mind as we work through this problem. Okay, but if we want to find the angle between these two vectors, we're going to use that same formula we used in the previous example. Even though we're working with vectors in 3D, the formula remains the same. It looks like this. If you want to find the angle theta between two vectors, vector v and vector u, then cosine of that angle is equal to the dot product of those vectors divided by the product of the magnitude of those vectors. All right, so in this case, we're not working with vector v and vector u, we're working with vector A and vector B. So the way we're going to set up our equation in this example will be like this. We'll have cosine theta is equal to the dot product of vector A and vector B divided by the magnitude of vector A times the magnitude of vector B. All right, so that's the formula that we're going to use for this example. And so I'll just erase this other one here. We don't need that anymore. But we're going to need a couple things in order to find this angle theta, which is going to be the angle between vector A and vector B. We need to know the dot product of those two vectors, and we need to find each of their magnitudes. I always like to start with the magnitudes, so let's do that first. Let's find the magnitude of vector A, and let's find the magnitude of vector B. Now for vector A, we're going to take the square root of the sum of its components squared, and the components are going to be the coefficients of I, j, and k. So we have 4, 2, and then 1, right? If you just have k, then the coefficient is 1. So we have 4 squared plus 2 squared plus 1 squared. And we'll work on simplifying that then. But let's write out the magnitude of vector B first. We're going to be taking the square root of the sum of its components, which in this case are 2 and negative 3. The z component, of course, would be 0 since we don't have a k term. So we would write 2 squared plus negative 3 squared. And this is unnecessary, but I'm going to write plus 0 squared, just so that you can see that we are accounting for that z component, but really it's just 0, so we didn't even need to write that. But now if we simplify, 4 squared is 16. 2 squared is 4, and 1 squared is 1. So this is equal to the square root of 16 plus 4 plus 1. And 16 plus 4 is 20, plus 1 is 21. So this is equal to the square root of 21. That's the magnitude of vector A. And I don't believe that simplifies any further, so we're just going to leave it like that. All right, now for the magnitude of vector B, 2 squared is 4, negative 3 squared is 9, and 0 squared is 0. So this is equal to the square root of 4 plus 9, and 4 plus 9 is 13, so this is equal to the square root of 13. All right, so now we have the magnitude for each of our vectors. Now let's find the dot product between them. And the dot product of vector A with vector B will be equal to the sum of the product of their corresponding components. And so what does that look like? Well, we're going to be multiplying the x components together, and then we'll add that to the product of the y components, and then we'll add that to the product of the z components. All right, so here's what that looks like. We'll have 4 times 2. Those are the x components. So we have 4 times 2. Then we'll add that to the product of the y components. So we have 2 and negative 3, right? So we'll have 2 times negative 3. And then we'll add that to the product of the z components, which are 1 and 0. So that's just going to be 0, but I'll write it out anyway. We'll have 1 times 0. All right, like I said, that's just going to become 0, so I'm not even going to worry about that. 4 times 2 is 8, and 2 times negative 3 is negative 6, so this is equal to 8 minus 6, which is equal to 2. And so 2 is the dot product of A and B. And so now we have everything that we need to set up this equation. So let's do that. We'll have cosine of theta is equal to the dot product of vector A and vector B, which is 2. So we'll have 2 divided by the magnitude of vector A times the magnitude of vector B. So we'll have the square root of 21 times the square root of 13. All right, so we'll write the square root of 21, and we're multiplying that by the square root of 13. Okay, now if we simplify, to multiply these two square roots together, we can simply just multiply 21 by 13 and keep it under the square root. And 21 times 13 is 273. And so we have cosine theta is equal to 2 divided by the square root of 273. Now, if we want to solve for theta, what we have to do is take the inverse cosine of both sides of the equation. And I like to express that as arc cosine. So we'll have arc cosine of 2 divided by the square root of 273. Right? If you take arc cosine of both sides of the equation, it will cancel out with this cosine and just leave us with theta. That's how we solve for it. And then we have arc cosine of this expression right here. Okay? And so now if you plug this into a calculator, you will find that theta is equal to 1.45 radians. And I did round that off a bit. I typically like to round off to 2 decimal places, but you can include as many as you'd like. That's just how many I choose to show. And then if you want to convert that into degrees, then your angle theta is 83.05 degrees. All right, and so that is the angle between vectors A and B. And if you're not sure how to convert from an angle in radians to an angle in degrees, I'll just tell you how to do it really quickly. All you have to do is take your angle in radians and multiply it by 180 divided by pi, and that will give you your angle in degrees. Okay, so in case you forgot how to do that, that's how you do it. And the angle between our two vectors is 1.45 radians, or 83.05 degrees. So for our next example, we have if the magnitude of vector v is equal to 40, the magnitude of vector w is equal to 25, and the angle between vector v and vector w is pi divided by 6 radians, find the dot product of vector v and vector w. All right, now this might initially seem like a complicated problem because we're asked to find a dot product of two vectors whose components we don't know, right? Typically when we calculate a dot product, we take the sum of the product of the corresponding components. We take the product of the x components, add that to the product of the y components, and then if our vectors are in 3D, we add the product of the z components. But in this case, we don't know any of the components of vector v and vector w. All we know are the magnitudes of those vectors and the angle between them. And so this is where we can make use of a very nice formula known as the alternate form of the dot product. It will allow us to find the dot product of two vectors given that we know the angle between them as well as their magnitudes. And that formula looks like this. The dot product of two vectors, vector v and vector u, is equal to the magnitude of vector v times the magnitude of vector u times cosine of theta, where theta is the angle between vector v and vector u. So in this case, if we want to find the dot product of vector v and vector w, it will look like this. We'll have vector v times vector w or the dot product of those two vectors, and that will be equal to the magnitude of vector v times the magnitude of vector w times cosine of the angle between those two vectors. And I'm going to use a different color for the angle this time. I'll make it look like this. And we know that the angle between vector v and vector w is pi divided by 6 radians. So I'll write that down here. That's the angle between our two vectors. Okay, so now all we have to do to calculate the dot product of these two vectors is just plug in everything we know and evaluate. All right, so this will be equal to the magnitude of vector v times the magnitude of vector w. So we'll have 40 times 25, right? Those are the two magnitudes of our vectors. We were given that in this problem. So we'll have 40 times 25, and then we're multiplying by cosine of the angle between those two vectors, which is pi divided by 6. And so we'll have pi divided by 6. Okay, now let's simplify. 40 times 25 is 1,000. So this is equal to 1,000 times cosine of pi divided by 6. And you might have this memorized. If not, just plug it in your calculator. But cosine of pi divided by 6 is the square root of 3 divided by 2. And so if we simplify that, 1,000 divided by 2 is 500. So we have 500 square roots of 3. And that is the dot product of vector v and vector w. Okay, we didn't have to use the traditional formula. In fact, we couldn't even use it if we wanted to. We don't know the components of vector v and vector w in this problem, and so using this alternate form of the dot product was pretty helpful here. Okay, so be on the lookout for scenarios like this, where you know the angle between two vectors and you know their magnitudes. You can use that information to find the dot product of those vectors. Okay, let's take a look at a different example. Next up, we want to show that vector v and vector u are orthogonal, where vector v is equal to 3i plus 2j plus k, and vector u is equal to 2i minus 3j. Now, what does it mean for two vectors to be orthogonal, right? What does that word mean? Well, in Calculus 3, the word orthogonal is just a fancier way of saying perpendicular. All right, so if you're asked to show that two vectors are orthogonal, what you're really being asked to do is show that the two vectors are perpendicular, that they meet at a 90-degree angle. All right, and in an earlier example in this video, we kind of already talked about this. In fact, we found that the angle between two vectors was a 90-degree angle, that those vectors were perpendicular. And what I said at the end of that example is that when the dot product of two vectors equals 0, that you will always be able to make that conclusion. All right, so if we're asked to show that two vectors are orthogonal or perpendicular, all we have to do is calculate their dot product. Okay, so let's take vector v and multiply it by vector u, right? Let's just take the dot product of these two vectors. So we'll start by multiplying the x components together. So we'll have 3 times 2. So we'll have 3 times 2, and then we'll add that to the product of our y components. So we'll have 2 times negative 3, right? So we'll have 2 times the negative 3, and then we're going to add that to the product of the z components, which will be 1. That's the coefficient of k. And then vector u doesn't have a k term, which means that the z component is 0. And so we'll have 1 times 0. Okay, so now let's simplify. 3 times 2 is 6. 2 times negative 3 is negative 6. And of course, 1 times 0 is 0. So this is equal to 6 plus negative 6 plus 0. 6 and negative 6 are going to cancel each other out, right? 6 minus 6 is 0. And so we have 0 plus 0, which means that this is equal to 0. And so because the dot product of vector v and vector u is 0, we have just shown or proven that they are orthogonal. They are perpendicular to each other. The angle between vector v and vector u is pi divided by 2 radians, or 90 degrees. Okay, and so if you wanted to, you could also write this. You could write that vector v is perpendicular to vector u. That's just a nice little way to express that that is true. This little symbol right here means perpendicular. Okay? Let's take a look at another example. All right, so next up we want to determine if vector c and vector d are perpendicular, parallel, or neither. All right, and vector c is equal to the position vector of the point 2, negative 4, 2, and vector d is equal to the position vector of the point negative 1, negative 1, negative 1. All right, and so if we want to determine if these two vectors are perpendicular, parallel, or neither, we need to understand what it means for two vectors to be perpendicular or parallel. And so what would have to be true about vector c and vector d for them to be perpendicular? Well, if you just watched the previous example, then this one might be pretty obvious. These two vectors will be perpendicular if their dot product is 0. But what about parallel? How do we know if these two vectors are parallel? Well, they'll be parallel if we can show that they are scalar multiples of each other. All right, another way that you could do that is to show that these two vectors would have the same unit vector. In other words, they have the same direction. Because if two vectors have the same direction, they'll never touch, which means they're parallel. All right, and I can see right off the bat that that's going to be impossible. These two vectors definitely don't have the same direction. And the way I can tell that is from the signs of the components, right? If you look at vector c, we have 2, -4, 2. The y component is negative, but then for vector d, all three components are negative. And so that's a problem because if we were going to show that these two vectors are scalar multiples, it's not going to be possible. You can't take out any scalar value from these components such that you will have the correct signs, right? You'll never be able to pull out a scalar or a factor out of these three components that's positive and end up with three negative components. And you also can't take out a negative scalar or a negative factor from these components and end up with three negative components. If you took out a negative factor out of these three components, this component would become negative, this component would be positive, and this one would be negative. All right, so since these signs alternate for these components, it's impossible for you to ever have all three of them with the same sign. So you'll never be able to show that vector c is a scalar multiple of vector d, or vice versa. It's just not going to happen. All right, so we can already eliminate the idea that these two vectors might be parallel. That's not going to happen in a million years. But these two vectors do have the potential to be perpendicular. And so let's see what happens if we take their dot product, right? Let's calculate the dot product between vector c and vector d, and if it's equal to 0, then we can conclude that they're perpendicular. And so let's take the sum of the product of their corresponding components. We'll start with the x components, so we have 2 and -1. So I'll write 2 times -1. Then we'll add that to the product of the y components, so we have -4 and -1. So I'll write -4 and -1. And then we'll add that to the product of the z components, which are 2 and -1. So we have 2 times -1. All right, now let's simplify. This will be equal to 2 times -1, which is -2, plus -4 times -1, which will be +4, and then we're adding that to 2 times -1, which is -2. And so we have -2 plus 4, which is +2, plus -2, which is 0. All right, so this is equal to 0. The dot product of vector c and vector d is 0, and so we can conclude that these two vectors are perpendicular. All right, so vector c is perpendicular to vector d. The angle between those two vectors is pi divided by 2 radians, or 90 degrees. Okay, and so that's it for this example. We were able to determine that these two vectors are perpendicular. Let's take a look at another example. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. All right, so here we have a similar example. We want to determine if vector x and vector y are perpendicular, parallel, or neither. So once again, we have two vectors and we want to determine if they're perpendicular, or if they're parallel, or if they're neither of those two things. All right, and so remember, if these two vectors are parallel, what that means is that they have the same direction, the same unit vector, which would also mean that they are scalar multiples of each other. And if they're perpendicular, their dot product will be 0. All right, now if we start with looking at if they're parallel, right off the bat, I'm pretty sure that's not going to be possible because if you look at vector x, there is no I term, right? We have j plus 6k. Vector x doesn't have an x component. So if we were to write that out in standard form, vector x would be equal to 0, 1, 6, right? We're just taking the coefficients of I, j, and k. There is no I, so the x component is 0. The coefficient of j is 1, and the coefficient of k is 6. So that's vector x. And then vector y, if we write it in that form, will look like this. We'll have 1, -2, -1, right? The coefficient of I is 1, the coefficient of j is a -2, and the coefficient of k is a -1. Looking at the components of these two vectors, it's going to be impossible for us to show that they are scalar multiples and have the same direction. Because the x component of vector x is 0, that makes it impossible for us to take out a scalar from the components of vector y such that the x component becomes 0. All right, and if you weren't sure about that, if you had no idea if these two vectors could be parallel or not, your backup plan is always just to check to see what their unit vectors are. All right, you find the unit vector in the same direction as vector y and the unit vector in the same direction as vector x and see if they're the same. If they have the same unit vector, then they're parallel, but if they don't, and they won't in this case, then you know that they're not parallel. And if you need a refresher on how to find those unit vectors, be sure to check out my lesson on unit vectors where I show you how to do that. Okay, so we know that these two vectors are not going to be parallel. That's out of the question. But are they perpendicular? Well, to check that, we have to take their dot product. So let's do that. We're going to find the dot product of vector x and vector y, and if it's equal to 0, then we can determine that they are perpendicular. Now, if it's a value other than 0, then they won't be perpendicular, and so our answer is going to be neither, that these two vectors are not perpendicular and they're not parallel. So let's see what happens here. Let's see what we get. We're going to be taking the product of the x components, adding that to the product of the y components, and adding that to the product of the z components. So we'll have 0 times 1, 0 times 1, then we'll add that to 1 times -2, so we'll have 1 times -2, and then we'll add that to 6 times -1. So we'll have 6 times -1. Now if we simplify, 0 times 1 is 0, so we have 0 plus 1 times -2, which is -2, and then we'll add that to 6 times -1, which is -6. And so we have 0 plus -2 plus -6, which is equal to -8, and that is definitely not equal to 0, and so we cannot conclude that these two vectors are perpendicular. They're not going to make a 90-degree angle with each other. All right, so they're going to have some other angle between them that's not a right angle, and so perpendicular is out of the question here. These two vectors are just simply not perpendicular and not parallel. They are going to be neither. Okay, and so with that, that's it for this example, but let's take a look at one more example for this video. All right, so here's our last example. We have given the vertices of a triangle below, determine if the triangle is an acute, obtuse, or right triangle. All right, so this is a little bit of a different example than what we've looked at so far in this video, but it is very much rooted in the idea of the angle between two vectors. And so to get started here, the first thing I want to do is draw a picture of what we're working with here. We have three vertices that are going to make up a triangle, and I'm not going to draw an accurate sketch or anything of these vertices in 3D. That's not going to be necessary. We don't have to do that. But what I am going to do is label each of those vertices and then just draw a generic triangle for us to kind of reference. All right, so I'll say that this is point A, this is point B, and this is point C. And so if these are the three vertices of a triangle, let's say our triangle looks something like this. We'll say that this is point A, this is point B, and this is point C. All right, and this triangle, like all triangles, has three different angles. We're going to have an angle in this corner where vertex A is. We'll have another angle in this corner where vertex B is, and then we'll have a third angle in this corner where vertex C is. And I'm going to label those like this. I'll label the angle here as theta sub A. I'll make this angle theta sub B, and this angle theta sub C. And what we want to do here to determine if this triangle is an acute, obtuse, or right triangle is determine what type of angles we have in this triangle given these vertices. If it's a right triangle, then two of the angles will be less than 90 degrees and one of them will be 90 degrees, right? Because a right angle is 90 degrees. So if you have one angle that's 90 degrees, then it's a right triangle. An obtuse triangle will be a triangle with two acute angles, and then one angle will be an obtuse angle, meaning it's greater than 90 degrees. And then if we have an acute triangle, then all three angles will be less than 90 degrees. All right, they'll all be acute angles. And so how are we going to determine what type of angles we have here? Well, for one thing, we're going to need to create some vectors. All right, because if we can define some vectors between these sets of points, then we can determine the type of angle we have between those vectors using the dot product. And here's what I mean by that. In my lesson video, I introduced some rules regarding the dot product and what it says about the angle between two vectors. And here are those rules. We're going to be focusing on the three in the middle here. We're not so worried about these two on the ends. Since we know we're working with a triangle here, we know our vectors are not going to be parallel. They're definitely going to intersect. So they're not going to be in the same direction or in the opposite direction. We're not going to have parallel vectors in any way here. We're going to have vectors that create some type of angle described by these three middle cases. All right, when the dot product of two vectors is less than 0, then we're working with an obtuse angle between those vectors. When the dot product of two vectors is 0, then those two vectors are perpendicular. We've been using that throughout this video. The angle is 90 degrees. And if the dot product between two vectors is greater than 0, then we have an acute angle between those two vectors. Okay, so just try to remember these three rules here. If the dot product is 0, they're perpendicular. If the dot product is less than 0, we have an obtuse angle. And if the dot product is greater than 0, we have an acute angle. Okay, so now let's go back to our problem. Now that we know where we're headed with this problem, let's actually create some vectors. We'll have a vector from point A to point B that we'll call vector AB. Then we'll have a vector from A to C that we'll call vector AC. And then we'll have a vector from B to C that we'll call vector BC. All right, so let's write those out here. We're going to have vector AB, vector AC, and vector BC. And to find each of these vectors, what we need to do is use the coordinates of their initial and terminal points, which are these vertices here, and find those vectors in component form. All right, so let's do that for vector AB here to start. Remember, you subtract the coordinates of the initial point from the coordinates of the terminal point. So we subtract the coordinates of point A from point B. So we'll have 0 minus 1, which will give us negative 1. Then 0 minus 2, which will give us negative 2, and then 0 minus 0, which is 0. All right, so that's vector AB. Now for vector AC, we'll subtract the coordinates of A from C. So we'll have negative 2 minus 1, that's negative 3. Then we'll have 1 minus 2, that's negative 1. And then we'll have 0 minus 0. So we have 0. Okay, and now finally vector BC. We'll subtract the coordinates of B from the coordinates of C. But if you notice, point B is just all zeros, so we're subtracting 0 from each of these coordinates. So they're not going to change. We're just going to have negative 2, 1, 0 as our components for vector BC. All right, so those are our three vectors that we're going to work with here. And we might need to make some adjustments to them as we go along, and I'll explain what I mean by that. But let's start by determining what type of angle A is. Right, the angle in this corner where vertex A is located. And the way we'll do that is by taking the dot product of vector AB and vector AC. It's important that those two vectors that we're trying to find the angle between both have the same initial point. All right, that's going to be important later on. In this case, we're good because both vector AB and vector AC start at vertex A. So we are looking at the correct angle between those two vectors. All right, but here's what we're going to do. We're going to take the dot product between vector AB and vector AC. So let me write that here. That's going to be equal to the sum of the products of their corresponding components. So we'll start with the x components. Negative 1 times negative 3 is positive 3. So we'll have 3 plus the product of the y components. Negative 2 times negative 1 is positive 2. and then we're adding that to the product of the z components, which are both 0, so we're just adding 0. So 3 plus 2 plus 0 is equal to 5. Now, here's where those rules from earlier come into play. The dot product of these two vectors is 5, which is greater than 0, which means that the angle between these two vectors, this angle right here, is an acute angle. The dot product is greater than 0. All right, so this angle right here, we now know is acute. That means it's less than 90 degrees, less than pi divided by 2 radians. Okay, so that takes care of this angle. That doesn't really tell us anything. An acute, obtuse, and right triangle all are going to have at least 2 acute angles. We're going to have to look at our other angles to see what type of triangle this is. And so let's move on to this angle, angle B. And we need to be careful here. If we're going to take the dot product between two vectors to determine what type of angle we have here, both of the vectors need to begin at this point B, which the two vectors we have drawn here are not. Vector AB is pointing towards point B, and vector BC is pointing away from point B. So we're going to leave vector BC alone, but what we need to do is flip the direction of vector AB. Or in other words, we need to look at vector BA. And that's pretty simple to find. We'll just take vector AB and multiply it by -1. We'll just negate that vector and we'll have the vector in the opposite direction. All right, and so what we want here is vector BA. And that will be equal to 1, 2, 0, right? We just negated each of these components. -1 becomes +1, -2 becomes +2, and 0 just stays the same. And so this right here would be this vector, vector BA, okay? It's pointing in this direction. It starts at point B, and so now both this vector and vector BC start at point B, so when we take the dot product of those two vectors, we will be looking at the correct angle, okay? So let's do that. Let's take the dot product of vector BA and vector BC. That's going to be equal to the product of the x components, 1 times -2, which is -2, plus the product of the y components, 2 times 1 is +2, and then we're adding that to the product of the z components, which are both 0, so we're adding 0. Now if we simplify, -2 plus 2 is 0, plus 0 is 0. So the dot product of vector BA and vector BC is 0, which means that those two vectors, this vector and this vector, are perpendicular. They make a right angle of 90 degrees, or pi divided by 2 radians. So we now know that this angle is a right angle, which means that we can make the conclusion that we have a right triangle. That is going to be the right answer to this problem. This is a right triangle because one of the angles is a right angle, since two of the vectors that would create this triangle, given these vertices, have a dot product of 0. All right, so we could stop right there, but just to show you that the other angle would be acute, because if you have a right angle, then the other two need to be acute, let's just quickly look at the angle between the vectors that would start at point C, which, by the way, we're going to need to reverse the direction of vector BC and AC to do that. We need vectors CB and CA. We need two vectors pointing out from that vertex to look at the angle between them. All right, so we're going to be looking at vector CA and vector CB. We just have to negate the components of their vector in the opposite direction. So we'll have +3, 1, 0, and then +2, -1, 0. All right, so we just changed the signs of the components, except for 0, of course. 0 just stays the same. Okay, so this is vector CA, and this is vector CB. We now have two vectors starting at point C that we can use to look at the angle between them. And so what we'll do is take the dot product of vector CA and vector CB, and that will be equal to 2 times 3, which is 6. So we'll have 6 plus -1 times 1, which is -1, plus 0 times 0, which is 0. All right, we have the product of the x components, the product of the y components, and the product of the z components. 6 plus -1 is 5, so this is equal to 5, which is greater than 0. And so we now know that this third angle, the angle corresponding to vertex C, is also an acute angle. Okay, so our conclusion was correct. we have a right triangle where one angle is a right angle and the other two are acute. Okay, and so a right triangle is the final answer to this problem. That is the type of triangle that is formed by these three vertices. And so with that, that's it for this example, which was the last example for this video. But if you do want to see another example, I do have more available on my membership site, so feel free to look into becoming a member if that interests you. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I have for now, so I will see you next time.